Dear students, let us continue the study of this paper, which is Organic Chemistry 1, and in this particular module we shall study about resonance, conjugation and cross conjugation. In the previous module we have already studied about the important electronic effects, which is inductive and mesomeric effects, and in this particular module we shall further understand the resonance, the conjugation, cross conjugation, and we will also compare them. Dear students, after studying this module, you shall be able to revise the concept which you are already familiar, that is resonance, and understand the terms conjugation and how it leads to resonance, and also learn about cross conjugation, which may be a new term to you. And then we shall be able to differentiate between conjugation, cross conjugation and non conjugation. So let us begin, dear students. Resonance, conjugation and cross conjugation, they may appear to you as very similar terms, but we should be very clear in understanding what is resonance and how conjugation leads to resonance and how the cross conjugation differs from conjugation. Further, we also must know what are the requirements that resonance is exhibited in the molecule and how this can bring stability. So let us try to understand and explore all these in more detail. Let us begin with resonance. Most covalent molecules, they have unique Lewis formula or the dot structure that you are already aware. These Lewis formula explain the bonding in that molecule, but for many molecules 2 or more dot structures are feasible rather than only one structure. The phenomena of resonance was put forward by Heisenberg to explain the property of such covalent molecules or species that could not be represented by a single structure. For example, let me take a very familiar example that you are already aware of. Consider this formate ion. The formate ion, as you can see here, can be represented by 2 equivalent structures. It can be where this particular oxygen is having minus charge or the other oxygen is having minus charge, and correspondingly the double bond gets shifted to the other CO bond. So of these structures, for formate ions, none exactly describe all the properties of the molecule. Here each of the 2 structures contribute to the true structure of the molecule, and such different structures are called as resonance structure or resonating structures. And the actual molecule is termed as the resonance hybrid of all these structures. So in this case, the actual structure of formate ion will be resonance hybrid of these 2 resonance structures. So resonance structures are simply alternate Lewis structures for a given ion or molecule. The actual molecule is found to be energetically more stable than would be expected from any of its resonance structures, and this difference is measured in terms of resonance energy. So how to define resonance energy? Resonance energy is defined as the energy difference between the most stable resonating structure and the resonance hybrid structure. Resonance is very common and significant feature of many organic molecules. Due to its presence, there is a pronounced influence on the structure, chemical reactions and physical properties of such molecules. In order to understand resonance, one must be able to draw the contributing resonance structures and the resonance hybrid structure. So let us now try to understand some characteristic of resonance and resonance structures. The first characteristic is that resonance exists only in those parts of the molecules that are composed of sp or sp2 hybridized atoms, and where the p orbitals are an absolute requirement for resonance. Hence, it is not taking place or it does not occur in sp3 hybridized atoms. The next point is, all the atoms in the molecules taking part in resonance should be coplanar. That is, they should be all in the same plane. And this is necessary for effective overlap of p orbital, because if the p orbitals are all aligned in the parallel direction, then only the resonance will be effectively taking place, not where one p is like this and other p is perpendicular to it. While making a resonance structure from other, electrons move between adjacent atoms. The type of electrons that can be moved are lone pairs or the pi electrons, which can also be there from a negative charge, or the unpaired electron present on radicals. These electrons, they reside on a resonance donor atom and move towards the resonance acceptor atom, which must be adjacent to the donor atom. The acceptor atoms must also have an open octet, be able to or have another electron pair, so that it can be further displaced. An atom with a formal positive charge can also be a resonance acceptor atom, as long as the atom does not accept more electrons than it can normally accommodate in terms of keeping the octet completion in mind. So, as you can see here in this particular graphic, that this particular C is having this minus charge, and so this can act as a resonance donor. The curved arrow here is indicating the shift of electron pair, and the other C, which is having a plus charge, will be acting as the resonance acceptor. So, as these two electrons move here, you can make that this will be the ethene. So, you can say this is the resonating structure for ethene, where these pi electrons, if they shift to either this carbon or this carbon, you will be getting this particular resonating structure. Moving further to more characteristics, the resonance structures or the contributing structures do not have real existence as individual species. This you always should keep in mind. These are only imaginary structures proposed to explain the properties of the molecule, and none of these resonance structures can be prepared in the laboratory. So, in real sense, the resonance hybrid is the real structure, and due to the resonance phenomena, the bond lengths in resonating structures, they exhibit equal values, that is, they become equal. For example, if you consider the case of benzene as a very simple molecule, in the resonance hybrid structure, as you can see here, the CC bonds are not alternate single and double bonds as in the resonance structures, which are these two. So, in the resonance hybrid, all of these bonds are actually the intermediates of single and double bonds, and that is why all the bond lengths are equal in this particular resonance hybrid. So, this is the resonance hybrid which is defining the real structure, not the resonating structures. The resonance hybrid has the lower energy and thus greater stability than any of the contributing structures. This is also very, very important. And also we can say greater is the resonance energy, greater is the stability of the molecule, and that is the reason why now you can see more is the resonance, greater will be the stability which will be achieved by that very particular molecule. So, for the resonating structures, the position of the nuclei must be same in all the structures, and the total charge must also be constant. This is also very important requirement while writing the resonating structures. Those structures have little contribution where the negative charge, when separating charge giving rise to ions, is on less electronegative elements. All resonance structures must have the same number of unpaired electrons, and the structures with similar charges on adjacent atoms are insignificant due to electrostatic repulsion and consequent instability. Resonance structures with greater number of covalent bonds are more stable. Thus, non-polar structure of formic acid is more stable than any other resonance structure. But when you are counting this aspect, always keep in mind that the octet violation should not happen of any of the involved atom. So, for example, you can see here these two formic acid resonating structures, and the neutral formic acid has more stability than this particular charge species. Another point or characteristics of resonance is that charge separation structures are less important than those in which the charge is delocalized. So, you can say wherever there is more delocalization, that is more stability, rather than simply you delocalize or separate the charges. And this is due to the electrostatic attraction between the unlike charges. So, we can say in case of ethene, when you put the pi electrons on either of the two carbons and you get C plus and C minus, that structure will be less stable as compared to if you look at this case, which is the acetate anion, where the O minus is moving from one to other. So, it is the one negative charge, but it is more delocalized rather than the charge getting separated in case of ethene. Now, let us look at some examples where we look at what is the correct way and what is the wrong way of moving electrons, so that you become more familiar at that how you can make these movement of electrons to write the resonating structures. Look at this first case. You can see that this C minus can be the C minus, which is minus is having 2 electrons. So, these 2 electrons move between these 2 carbons, and as a result further the C double bond O, the pi electrons move to the oxygen, and you get this particular resonating structure. So, this is a correct way of movement of electrons. Let us look at this next case. Here the nitrogen has the lone pair. So, these lone pairs are free to move. So, they will be moving to the adjacent bond, which is NC. The C is having plus charge. So, the plus charge gets shifted to the nitrogen, and C has its full valency and there is no charge there. So, you get this particular structure where nitrogen is plus, and keep in mind the octet is still complete for the nitrogen, that is after giving or accepting that violation should not happen. Let us look at the next structure here. Here again the nitrogen has a lone pair which will move to the adjacent bond, and in turn the C double bond O pi electrons get shifted towards the more electronegative oxygen, and you get C single bond O minus. So, this is the resonating structure that you get. Look at another example. Here the double bond is in conjugation with a carbon having plus charge. So, carbon having plus charge is electron deficiency. So, these 2 electrons move towards the adjacent bond, and as a result the terminal carbon gets electron deficiency, that is now in the resulting structure the plus charge is on that, and double bond has shifted to this particular position. Let us now look at some cases where there is a wrong movement of electrons done. Look at this first case. Here the shifting is being done of the lone pair are there on oxygen, but if they are shifted here, you are getting C with minus and O with triple bond plus. O with triple bond plus, you may say it is still okay, but C is having octet violation. So, this is a wrong movement of electrons that has been done. Looking at another case, here again these pi electrons, if you say they are shifted towards this particular CC bond, this is again a wrong way, because already there is a C minus. So, preferred movement will be C minus would have moved towards the C double bond O, leading to O minus, and not as done here where C is getting 2 minus and O is getting plus. So, keep in mind the molecules are rearranging, undergoing resonance, there is a rearrangement of simply the shifting of electrons, the delocalization of electrons which is happening, and all that will happen where it will bring stability to the molecule. Obviously, the molecule will not go into a position where it becomes unstable. So, let us now move to another aspect of resonance, is the most important resonance contributor. During an organic reaction, many molecules exhibit resonance. When writing the mechanism for the reaction, the best representation of reality can be depicted by using the resonance hybrid structures. However, because the resonance hybrid does not show explicitly the electron pairs that are shared by resonance, its use in mechanism can be unclear and confusing. Thus, we often use a single resonance contributor instead of the resonance hybrid. But then the question comes, which one has to be used? When deciding which resonance contributor to be used, we must consider that one that makes the greatest contribution to the resonance hybrid. And obviously, that would be one which is most stable of the possible canonical structures. So, let us try to understand how to compare the resonating structures in terms of the stability, that is the resonating structures of the same species in terms of their stability. So, for this we need a set of rules to determine the most important resonance contributor, and these rules are based on the assumption that had the resonance contributors actually existed, the most thermodynamically stable structure would have made more significant contribution to the resonance hybrid. Factors that increase the thermodynamic stability are maximization of covalent bonding and minimization of charge. Resonance increases stability by increasing the bonding between adjacent atoms and by distributing charge over a greater number of atoms. So, what are the rules to be followed to compare the stability of the resonating structures? Note that you have to check them in a sequence. So, first point first, apply to the molecule, then the second, then the third. So, the first parameter to be checked is that a neutral molecule is more stable than a charged one. And this is very obvious that a neutral molecule shall be more stable than its resonating species in which charge separation is there. Next parameter comes is a species having maximum number of atoms with full octet is more stable than others, and this preference gets priority over the other rules which will be subsequently following for determining the most important resonance contributor. For example, out of these two species A and B, you can see here the CH2 is having plus, and the moment these lone pairs can be shifted here, you get this species B. The carbon of the structure A has an open octet, it is incomplete octet. Note that there are 6 electrons in this carbon, and all the atoms of this structure B, note that they have complete or full octet. Therefore, out of A and B, B is more important than the contributor A, although the positive charge is on the more electronegative oxygen atom instead of the less electronegative carbon atom. So, this aspect should not confuse you. So, you have to sequentially follow these rules to get the answer. The third parameter in sequence you have to check is the electronegative atoms having negative charge is more stable than having positive charge over them. Electropositive atoms in turn having positive charge is more stable than if they are having negative charge, and this is again obvious, but this is not to be looked at as the first condition. You have to sequentially follow, and this becomes the third parameter to be looked. For example, look at these two particular species C and D, which are resonating structures, and out of C and D, it is the D which is more stable, as the electronegative oxygen atom is having negative charge in case of D, but in case of C, it is the electropositive carbon which is having a negative charge. After this, let us take one example and compare the stability of some resonating structures, and let us take the case of formic acid. So, you can see here these are the 4 resonating structures of formic acid, and out of the 4, clearly first is most stable. You apply the first parameter, that a neutral molecule is more stable than the charged species, and rest all are charged, that is why the first is most stable. Out of the remaining, you can notice the 4 is more stable, as it has all the atoms with complete octet, the parameter 2. And caution here, do not get carried away by the positive charge on oxygen atom to mark it as least stable. Remaining 2 are second and third. Out of second and third, second is more stable, as it contains electronegative atom oxygen which has negative charge, and electropositive carbon which has positive charge, and it is other way round in the structure 3, and that is the parameter 3. So, the overall stability order we get is first is most stable, followed by fourth, followed by second, and followed by third. So, I hope the concept of resonance is very clear to you now. Let us now move to the next aspect, which is conjugation. Conjugation is the overlap of one p orbital with another across an intervening sigma bond, and in larger atoms even d orbitals can be involved. In molecules that contain more than one multiple bond, for example dienes having 2 carbon-carbon double bond, it is found that compounds in which the bonds are conjugated, that is alternate, multiple and single bonds, they are slightly more stable than those in which these bonds are isolated, that is they are not in alternate position. For example, out of these dienes, you can see the first one is the conjugated one, it is more stable than the second one, which is the non-conjugated one. So, conjugation means the alternate, multiple and single bond present, so that the resonance can take place. The largest conjugated systems, if we talk, they are found in graphite, conductive polymers and carbon nanotubes. A conjugated diene has a lower heat of combustion and a lower heat of hydrogenation, which experimentally justify for their more stability. Also, isolated double bonds can be often made to migrate very readily, so that they become conjugated. For example, you look at this particular case, this double bond is not conjugated with carbonyl, and by using a base catalyst, the double bond can be shifted to this position, which is the conjugated position to the carbonyl, and this is more stable and then the one we have started with. If we take some more examples as shown here, you can see the atoms that form the part of a conjugated system, they are shown in blue, and the ones that are not, they are shown in red. Notice that it is the sp3 hybridized atoms that break the conjugated system, which are being marked with red. So, all these blues, they are showing till here the conjugation is there, and then at red positions the conjugation is stopping. So, the electrons in a conjugated polyene are said to be delocalized, as they are now held in common by the whole of the conjugated system, rather than being delocalized over 2 carbon in a pi bond. Delocalization is involved in stabilizing the excited states of dienes and polyenes in general, that is in lowering the energy level of their excited states. The effect of this is to reduce the energy gap between the ground and the excited state of the conjugated molecules as compared with those containing isolated double bonds, and this energy gap is progressively decreased as the extent of conjugation increases. This means that the amount of energy required to effect the promotion of an electron from the ground to the excited state decreases with increasing conjugation. That is, the wavelength at which the necessary radiation is absorbed increases. Simple dienes absorb in the UV region, but the extent of conjugation increases. The absorption gradually moves towards the visible range and the compound then appeared colored to us. Let us consider the series of alpha omega diphenyl polyenes, which are represented by general formula C6H5 CH double bond CH whole N C6H5. Here when N is equal to 1, then these are colorless. When N is equal to 2 to 4, they exhibit yellow color. When N becomes equal to 5, the color becomes more intense, that is orange, and when N is equal to 8, then the color is even more intense, that is red. So you can clearly see that these dienes absorb initially in the UV region when N is 1, but then as the extent of conjugation increases, the absorption moves towards the visible range and the compound appears colored, and the color also keeps on intensifying. So after understanding conjugation, let us move to a new term which is cross conjugation. Now cross conjugation is a special type of conjugation in a molecule. But here out of a set of 3 pi bonds, only 2 interact with each other by conjugation, while the third one is excluded from the interaction. So a cross conjugated system has a double bonded unit, single bonded unit to one of the middle atoms of another conjugated chain. On the other hand, a normal conjugated system such as a polyene typically has alternating single double in the conjugative atoms. So you can see here this example where this is showing a molecule having cross conjugation. So you can see here at one particular time only either these 2 double bonds will interact or these 2 double bonds will interact. All the 3 double bonds cannot take part in delocalization together in a sequence. So in other words, one of the double bonds is like a branch of rather than continuing conjugatively. Hence, the main chain is conjugated and part of the same main chain is conjugated with a side group, but all parts together are not conjugated. So this type of conjugation is called as cross conjugation, and obviously this has an impact on the reactivity and molecular electronic transitions. Let us look at some examples. Some simple cases you can look is these 2 phenyl rings are there and in between there is a carbonyl. So this is a cross conjugation case where this carbonyl can take part in conjugation with either this phenyl at a time or the other phenyl at a time, but continuously these 2 phenyls and carbonyls cannot be in a conjugation. Similarly, look at this particular case. Here again these 2 double bonds and in between there is a carbonyl compound. So the total continuous delocalization is not there, but yes, in parts you can see this carbonyl can take part in delocalization with either this double bond or either the other double bond, and these 2 alkene double bonds cannot delocalize with each other. Similarly, another case is this molecule which is quinone. Here again it is a cross conjugation case. The carbonyl with the double bond and another carbonyl, this entire system can take part in delocalization where this other double bond is left out, and similarly this lower part can take where the upper one will be left out. But all these 4 pi bonded systems cannot take part in delocalization in a continuation format. Another set of examples are the dendralenes. A dendralene is a discrete acyclic cross conjugated polyene. You can look at these structures 1 and 2. The simplest dendralene is the buta-1,3-diene, which is 1, or it is called as 2-dendralene. The next one is 3-dendralene, which is the structure 2nd. The next one is 4-dendralene, and the next one is 5-dendralene, which is the structure 4. And you can see why this abbreviation of 2, 3, 4, because in first there are 2 double bonds, in next one there are 3 double bonds, then the next one is 4 and so on. Notice that the 2-dendralene, which is the first structure, that is the butadiene, is the only one which is a conjugated system. It is not cross conjugated, but the rest, that is 2nd, 3rd and 4th, are the cross conjugated systems. They are not the conjugated systems. Another set of molecules which exhibit cross conjugation are the radialenes. These are the cross conjugated alicyclic organic compounds. They contain a cross conjugated exocyclic double bond. The double bonds are commonly alkene groups, but those with a carbonyl group, they are also called as radialenes. You can see here these structures are showing you, this is a 3-membered ring, the cyclopropane ring as the framework, and then there are 3 exocyclic double bonds. Then the next one has the 4-membered cyclic ring as the center, then the 5-membered ring and the 6th. So all these are the radialenes. So you have this as the 3-radialene where 3 double bonds, exocyclic double bonds are there. Next one is the 4-radialene, next one is the 5-radialene, and the next one is the 6-radialene. And all these radialenes, you can now understand they are all cross conjugated systems where all these double bonds cannot take part in conjugation at the same go, but yes, part by part you can look at there is conjugation present in these molecules. So after understanding cross conjugation, let us now do the comparison of conjugation, cross conjugation and non-conjugation. Conjugation comes in 3 flavors, the simplest of which is the normal straight through linear conjugation seen in many biomolecules such as vitamin A, as you can see here. You can notice all these alternate double and single bond. Here it will be providing conjugation to the molecule. However, it is possible for 2 systems to be in cross conjugation. Now you are already familiar with the term cross conjugation, and notice that in this structure there is a cross conjugation present because of this double bond which is a branch out. So either this part of the molecule is conjugated or this part is conjugated, but on the whole it is not conjugated. So the 2 benzene rings, you can say, are cross conjugated and they are not conjugated. So wherever there is no conjugation, the term obviously non-conjugation you can use. Conjugation is broken completely by the introduction of sp3 hybridized carbon atoms, that is a saturated carbon. As you can see in this particular case, this particular carbon here, here and here, you can see these 3 carbons are sp3 hybridized and they are breaking this otherwise conjugated system. So this becomes a no conjugation or non-conjugated system. So dear students, let us now summarize what we have learnt in this module. We studied about resonance, conjugation, cross conjugation and understood non-conjugation. Resonance is a very common and significant feature of many organic molecules, and we define resonance energy, which is defined as the energy difference between the most stable resonating structure and the resonance hybrid structure. We also studied that resonance increases stability by increasing the bonding between the adjacent atoms and by distributing charge over a greater number of atoms. We studied that a cross conjugated system has a double bonded unit single bonded to one of the middle atoms of another conjugated chain. That is, it will be a branch appearing in a conjugated system which will be giving you a cross conjugation. On the other hand, a normal conjugated system such as polyene typically has alternating single and double bonds along the conjugative atoms. And we also studied that conjugation is broken completely by the introduction of the sp3 hybridized carbon atoms.